So then, welcome to lecture or actually a little bit more exercise. So we'll do a little bit lecture and a little bit more exercise today. Number 7. So we'll continue first with what we have started last time, the calculation of pi. And we are going to do this with a divide and conqueror method. And then we'll look at a different problem that is, or different approach, including that is communication hiding. So we'll come to this later after we made our first exercise here. So, presentation. Okay. First, so in the first part of this, we are continuing with our calculation of pi that we can calculate by integrating the circle function and taking this times 4, because integrating the circle function, which is above here, will give us the area, and the area in this quadrant is of course pi, a quarter of pi. And by just using a simple integration rule, we can compute this. And in order to make this accurate, we need to have many evaluation points, and then we'll do this here in parallel. Okay. The part that everybody should have reached last time is the master and slave approach. And the master and slave approach is completely fine for this kind of problem. I'm a little bit in trouble today because I want to convince you of something which in the size of the problem that we can handle, is not visible. So you have to believe me. Yeah, so because we have a maximum of 20 these nodes. They have a maximum of 20 parallel processes, 20 processes, and with 20 processes, the master-slave approach is completely fine. Yeah, so one master deals with 19 slaves. Yeah, so no problem. Yeah, but you see, if the number of slaves gets larger and larger and larger and larger, at some point the master needs some kind of sub-masters. Yeah, because everything, so each slave, he is communicating with this one master. So the master is becoming the bottleneck because he has to manage all the slaves. Okay, for 19 slaves, everything is fine, but you could have many more slaves. Yeah, so you can do this. It's very politically awkward. This topic. Yeah, sorry. We'll continue with using the usual name for this. So the approach that is better when we have many workers is that we subdivide this in this tree fashion here, where we first say in the first step there is always one slave and one master, and just the slaves communicate with their own master, then the slave is free. Yeah, that's the good thing here. After the works, the slaves are free. But when a slave is free, it actually means it is destroyed as a program. Yeah, terminated, executed with signal 0. Sorry for that. So it gets. So after the master received from their slave, half of them become slaves themselves, and half of them become master, and so on, yeah, until only 2 of them are left. And now you see with this, how much, this was 1, 2, 3, oh sorry, 1, 2, 3, 4, 5, 6, 7, so we have 8, yeah, so this is, here we have a communication of, here the master has to communicate with 8 steps, and here all the slaves, and here the last master, so the master who is the 0 process, the king or the emperor, yeah, they have only to communicate with log 2n, which is of course a lot less than with n. So, and this is the thing that we now want to implement. And yes, so the way we are going to implement it, or has anybody already, because this was the homework, have you already all implemented this?
I tried it, but
it didn't work. Okay, let's think about how we are going to do this. So, you know, if you are a slave, your life is hard but simple. Yeah, so you just have to do your work, you deliver your work, and then you get executed. Yeah, or terminated. Yeah, then you execute yourself. Yeah, so but if you are a master, or if you're a temporal master, yeah, you have to collect work from the slaves. So say we look at this this process number 4. The process number 4 will first be a master in one step, then it will still be a master in the second step, and then it becomes a slave to the master. So what does it mean? It means it has to use a loop over its various slaves, yeah, to question its slaves for the return of their data. So this is step number 1. Okay, and this loop needs in particular increment. Yeah, okay, if I have a larger one, and we look at this here, for example, number 8, yeah, first gets their result from the immediate neighbor, then from 1 further on, then from 2 further on. And then in the next step, it would come from 4 further on. Yeah? So this is the destination index. Yeah, okay, this is where the slaves has to send their data. So basically we have to, let me see, no, this is the next one. Yeah, basically our challenge is to compute these indices. Yeah, so the indices from where, so we have to know who is our next slave, and the slave has to know who's my master. Okay, shall we give it a try? Let me see whether I be able to skip to, no, this is the wrong one, so this one. Okay. Now, last time, did you implement this master-slave version? So maybe if you haven't, or if you are not sure about your result here, so what you can do is you can pick this one here up. Wait, I'll do something before we'll pick this up. this is the solution. Okay, let's. Okay, you can. Now I killed the solution. You can pick the results or the starting point up in the folder PVE PVR 2024. Then you go to Gaia and then lecture 5. Sorry that it's lecture 5. And then there are similar things with similar names, but what we mean is main DAQ.cpp. Yeah, there you can pick it up. Don't change it there. Do a copy to your own folder. Okay, so this should be the file more or less that we implemented, or that you should have implemented last time already. Yeah, so there is again the integration function. Main. In the main, we initialize the MPI, so we have a number of processes, we have repetitions. We get to the rank, the size, and we start with a result equal to 0. Do some calculations of splitting up the domain, and then we call our local integral. After calling our local integral, we do here the master and slave approach. So remember, if the rank is not equal to 0, then we are a slave. Yeah, so then we do, we send our result to the receiver ID, and the receiver ID is always 0 because this is the master. Yeah, so it's the master ID. And if my rank is not equal to 0, so if it's 0, then we are the master. Then we do the receiving from everybody. We simply ask everybody and add up all the results. Right. So this is our divide. Sorry. No, this is. Why do I write divide in? Divide in. So I might just. Sorry for my dyslexia. Okay, everybody got that? Good. So now what we are now doing is we are not doing master-slave stuff, meaning we are taking this stuff here out. Let me see that I don't make a mistake now. So by pressing Control dash will make this a comment. Yeah. So and I made a comment from what we had here calculating the local integral. I'm just wondering whether I should have kept the local integral. No, okay. Okay, so this is where we are, and now, because I deleted the local integral, I have to redo the local integral. Let's just start from the local integral. Okay, so how's the local integral? I notice standing here is very inconvenient writing environment, so this means I'm typing very slowly. Maybe that's a good thing for you to follow. So we have the local integral is equal to the integral, so this is the function is defined below, of the local A, so this is the upper bound, and the local B, which is this is the lower, sorry, this is the lower bound, and local B is the upper bound. And then we get the local number of intervals, right? So this is something that we have already computed above, local number of intervals. So don't forget the semicolon. Why doesn't he know the local integral? Haven't I defined it? Double local integral equals then I mistyped it, right? Integral, yes. So, okay. So the local integral is defined up there, I guess, in line. Sorry for that. So all these things here, all the things that we have here in line 60, yeah. So 60 is where we was. They are defined here, and the local number of intervals is defined here, and we have local integral, double local integral, is defined here. So, and this is something that we said now. Now we are here back in line 60. So, okay. Now we want to get this into our result. So the result is the accumulator in which we accumulate all the local integrals, but my local integral is my own local integral. Yeah, right. Remember, the masters do the calculation too. Yeah, that you could also have so they also do the same part, that part of the work. We could, of course, also have a system where we where only slaves do the work, but now, now everybody is partly slave and partly master. This is why it's necessary that everybody does their work. So, and this means that the result, you see, I have to watch out. So we initialized the result with being 0. Oops, I'm sorry for that. Yeah, okay. So result so far only contains nothing, so I'll just say that the result is local integral. And now we need something, because I deleted everything, we need our receive buffer. So we have a double receive buffer. And for the communication, we also need a status. So we don't really need a status. MPI. This is something that we are usually not using here today. I mean, the function, the MPI functions, they take a status or a pointer to a status from which we can draw the status of the communication. That's something that we don't need to define here. What could we do instead if we are not interested in this in what is in the status? Yes, so there is an what is called wildcard, I believe. Yeah, so you can if you are not interested in this, you can tell them to ignore the status. This is one of the MPI constants. So now we decide that we have the status, and now what we want to do, now comes the actual work. Now we want to compute, we have to make this loop this loop here, our local loop. And in this local loop, of course, we have to compute the indices of the center. Yeah? Let me say okay, so what is the indice of the center? So here, the first center would have the indice 5, and the next one would have the indice 6. And then the next one would, if there was a next one, it would have an indice 8, right? But this, of course, depends on where we start from. Yeah, so what we actually have is our own index plus 1, our own index plus 2, and then our own index plus what? 4, and then our own index plus. Okay, so what is 2 times 4? 17. 8. Yeah. So it would be 4 plus 8, yeah? So 12, apparently. I'm not completely mistaken. I'm mistaken. Wait, it is 4 plus, no, I'm not, no, it's okay, yeah. Because, okay, so we go 1, 2, 4, 16, 32, right? Yeah, so this is our 4, 8. What did I say? Okay, 1, 2, 4, 8, 16. Okay, it's not on the recording that it's very hot today, yeah? Yes, so, right. Okay, so we'll have our own index plus this, what we call then an offset. Let us call this stuff an offset. Yeah, say we'll start with an integer offset. And we'll start with 1. Okay? Okay, and then we do this in a loop. Let me see. Why did I define it before? I don't know. Doesn't matter. For offset, so offset equal to 1. So now I put the offset in an outer scope. Offset equal to 1. So I don't need to redefine it as an integer because it's already defined. Offset is 1. Then we need to, so when do we, now we need a stopping condition. What is the stopping condition? Intervals? Yeah. So what is supposed to be larger than? Yeah, yes, so, okay. Okay, you know what? We'll just try out what you are suggesting, and then we see later. So, what are you suggesting? Yeah.
So the offset, the maximum offset would be.
So should I offset? Offset is smaller.
Should be smaller
Then?
The processes divided by 2.
How? So this was num processes, right? Number of processes. Okay, divided by 2.
I'm not sure if it's divided by
Offset is offset.
So I guess that the idea is in what we were trying to do here is just having the same number of cross. For example, we have 0, 2, 4, and 6. In the next step, the master should be 0 and 4, right?
We are looking for our, okay, so we are, at the moment we are looking for our slaves. I mean, we do a loop, yeah, the master does not, we are in this local, loop, where as long we are master, only the master is in a loop. And we are looking for our slaves. Yeah, so that's, so what we need here is the offset to our slaves.
So first iteration would be the step count would be 0. So 0, 1, 0, 3. Next time it will be 0, 2, 4. So it is incrementing by 2 raised to something.
It is, so okay, but what am I supposed to write? So offset, so this is the increment. So how do I increment?
So I think that the offset should be less than log to the base 2.
Okay, now we are, okay, so this is the halting condition, the, what is this? The Abbruchkriterium. Stopping condition, thank you. The stopping condition, yeah, but now my question was about the increment. Yeah, of course we need to get both right, but probably increment is easier than stopping condition. What is the increment? Offset times 2. Times 2. So this is the increment, yeah? So is everybody happy with offset is smaller than number of processes half?
I guess it depends on how we implement it, but I would put like.
Okay, should we try it out and remember that we try to revisit this later?
Okay, I didn't fully understand the scope yet, but if
It is not yet written.
Sorry?
The code is not yet written.
Yeah, the other part of the code, sorry, like the framework.
The framework. Well, the framework is that each of the process has their part, yeah, their slice that they integrate, and then we sum up the integral. Yeah, that is all we need to know.
Okay, so you're calculating like an iteration from top to bottom, like vertically? This
Vertically.
is vertically, right?
Okay, should we go back a little bit to the original, to this image? See, there are, okay, let's briefly return to this image, yeah? So there is a process, actually there should be a process 0, yeah? But say this is the first processor, the second processor, and the third processor, right?
Yeah.
So, and they, P1 is integrating this red part, yeah? So it needs, so the red part itself is again divided, so this is this inner loop, yeah, because the integration needs several steps, yeah. So this is why I draw 2 bars here, yeah. So this is like it divides its domain in a number of steps and does the integration over these steps. But this is locally and this does it in serial. So this is the inner loop here, the inner loop. And then there is the outer loop, which is now parallelized, and the work of the master, there is summing up these integrals. Yeah? So, now what we have done. What we have done is local integral. The local integral is now being calculated and is in local integral here in the line 60.
Can you go back to the image of the divide and conquer?
and divide and conquer. So,
Yeah, so about the slaves in step 2, are they doing any work or like some in
now the slaves,
the slaves that
okay, so we do see, what is not in this picture is the actual calculation. Yeah? Yeah, so everybody did their calculation, and all we are talking about is how we combine everything.
yeah. But
Yeah?
I mean in the first image, like the serial image, the master doesn't calculate anything. It just sums actually it calculates, it sums everything, but it doesn't integrate anything.
Interpret. Well, what is interpret?
In the first part, you get the curve, I guess, and you divide in intervals to the slaves.
Yeah.
Each slave integrates, like the.
And the master also.
The master also integrates.
Yes.
Oh, sorry. I thought it would just like.
No, yeah, because, so everybody here does their work on their own. Yeah? And this is not in this picture. In the picture is only when we combine everything. So when we put the pieces together. The initial work is not in the picture.
Okay.
Yeah? So this is, we are now only in this loop here. So we are currently trying to implement this loop here. That is doing this collection. So let me see. Maybe we'll not get to everything today but it's good that we have many questions. I like this. So okay. I mean this is now our state. Yeah? We are back here in line 65. Now we want to implement this this loop. Are we now happy with the no?
And the offset is 1, it is already smaller than the number of processes by half, so the condition can be smaller. So I guess.
Okay, so the offsets. Okay, so you want to have them
I guess equal maybe. Or bigger, yeah.
equal. Okay, well, equal, bigger, equal or bigger, equal or bigger.
This is the power of 2 orders.
I guess in this case it should be the same as.
Okay, so if
number of processes is a power of 2, then equal should work.
and otherwise,
Otherwise, the divide and conquer doesn't work.
then otherwise divide and conquer doesn't work. Okay, but then we are okay. Should we do? So wait, is this? So this way. Sorry. So if wait. This is the. There's the stopping. You know what? You're completely confusing me because this is not the stopping because we said stopping condition, but this is the running condition actually. It's the inverse.
Yeah,
So as it is doing the stuff as long as it is smaller.
generally,
Yeah, it's apparently really hot today, right?
generally I read this as a while, like while offset is less than like the while.
While.
Yeah, it's just like
Yeah, you can write each for loop in a while loop, if you will, yeah? So as long as this is, okay. Okay, maybe we visit this later. I don't know either. Where were we? So, actually all we want to do is now waiting for the message from our slave. So we have to do an MPI receive. Receive, yeah, and so now this takes the receive buffer. So there's a pointer to the receive buffer. So we have to take the address receive buffer. The length of what we are receiving is 1, right? So what are we receiving? What type? Double. No, yeah, right. But the MPI double, right? So in the exam you have to you're supposed not to write double but MPI double. Okay, so who is our slave now? Where are we expecting the stuff from? Our node number is my rank, okay? My rank and then plus offset. Okay, dokie. My rank plus offset. So then there is this tag that we have not actually been using, but we have to put it anyway. And then we need MPI communicator, which is usually mcom world. And then we need the status, or we have to write MPI status ignore, but now since we have introduced the status, we'll use the status, yeah? Pointer to status. Okay. Don't forget semicolon. So now we have received the stuff. What we have to do now is to do the integration, which means that the result, remember the result already includes our own integral, so the master has done their work first, right? So this result plus what we got into the receive buffer. Receive buffer. So now that should be that loop. That should be the receiver loop, right? Or is anything missing? Result plus equal. So you're hopefully familiar with this. Yeah, sorry for mistyping. Okay, so that should be that loop. Now the other one is, of course, we need, if we are a slave or if we become a slave, because when you were a master, you can become a slave. If you're a slave, you can never become a master. Then we need to know where to send to. Yeah, so this is probably very similar to what we had before. But this is now one on its own. Okay, so there is one so there's one guy who is never never a slave. Yeah, so I found this interesting in India. So there are many roads where there's a sign. So who can pass here? So the first thing is if you are the president of India, then you have free passage. Have you seen this kind of roads? Yeah. So now if the emperor if the emperor does not need to do anything. So say we excluding the kind of my rank is equal to 0. Yeah, so this is excluded because this is the only guy in the divide and conqueror that will never be a slave, right? Everybody else, if we go back, yeah, you see, everybody else runs into being a slave in the end, but only the master process is never a slave. Yeah? Okay, so this is why we exclude this. Okay, opening a scope. And now we need to calculate our receive index. So we need to know who is our master. How do we do this? Okay. Yes. Okay, we'll do the opposite. Okay, this is probably not the most elegant way of doing it, but you see, it's a solution. Yeah. Let's call this because I called it this way in my example here, so not in order for me to be confused. I call it IDX, which is short for index, yeah, of our master. We could also say master index. Should we write master index? Maybe I write master index. Master index. Okay, let's call this thing master index. Let's call this thing master index. Okay, and say the master index. My master
Rank minus offset. Rank minus offset.
What is? Okay, did you have an rank? My rank. You mean my rank? My rank. My rank. My rank minus offset. Okay, so is this everybody happy with this? So let me see. My rank minus offset.
The chances are you can run beyond, for example, if it's 1 and the offset is 2, so we can go minus 1.
Yeah, so I mean, the problem is, I mean, this is now not really the opposite of what we have done before. So if you want to, because if this worked, but this wouldn't work, if it worked, then it would be elegant, right? Because it's simple to calculate. I guess we do it. Let me see if there was a time. Okay, let's start this with 1 and do it a little bit less elegant, yeah? So we can do this because doing the opposite is again using you know, maybe I was confused, you know, because we get a new offset, yeah? Let's call it, because, yeah, so otherwise we get confusing. Don't call it index, call it master offset. So master offset. Right, so because master offset must be at least 1, right? Yeah, so because we are not in ourselves. Then we do it similar to before. So we have a master offset is equal to 1. Then doing what? What is the condition that we are still running? Okay, let's see the thing for doing the update is master offset. Maybe we start with this. So master offset. Master offset is what? Master offset is master offset.
Smaller than number of processes.
No, it's not. Yes, see, I kept this here empty. We first talk about the increment, and then we talk about the condition.
So times 2.
Times 2 again, yeah, so. Because it's easier to talk about the condition when we know what increment we have.
In this case, it should be the same condition.
The same condition, okay? So which,
We're not sure if it's divided by 2 or it just...
so you're saying we have the same condition here. Well, okay, let's have a try. You know, I don't know myself. Master.
I mean, you could start a master set like EDN and just divide by 2 steps, and then you have a different condition like it would.
Okay, so how do I start at the end?
You can initialize master set like with number of processes divided by 2, and then your step is dividing by 2, not multiplying by 2. So you're
Okay, but suppose, okay, yeah, there's, of course, you can always. No, it's not good. No, it's not good. It's not a good idea because we'll want to. Okay, maybe. Yeah, okay, there's always several possibilities. Yeah, of course. So if we want to do it the same way as before, then now you said we should use the same thing. Does it mean offset number that I should again write offset is number of processes divided by 2, okay? Is this what you want? Does this make any sense to anybody?
I would try to put just like number of processes and all of them. Because this should like have one last step, right? Like according to the step, you are doubling every time. So if you divide the condition by 2, you are doing one less step. And I'm not sure if this number of processes counts 0. So
The number of processes.
if you initialize an array in C++, for example, if you put like 3, it's 0, 1, and 2. So you shouldn't go to 3 because if you retrace,
You're running out of, okay. Yeah, but we are going, now what we want to go, so our problem would be if we go below 0. Yeah, because our master is left of us. You see that our master is always has a lower rank than we have.
Yeah,
The slave always has a higher rank. See, this is a good thing about this approach, that the slave has a higher rank than the master. Yeah, but here the the master has a lower rank.
Maybe we can put an if condition that only if the master index is above 0, only then send.
Well, why wouldn't I just send everything to 0 then? Then we are back in the usual master slave.
I guess the problem is because we are not differentiating that much masters and slaves. It's like just everything there. The only thing we're differentiating.
Okay, so let's see. Suppose we are this slave here. Yeah. So then we want to go to our to our next master. So this here will go 2 down. This here will go 4 down. By the way, we'll end so our master, see, our master still has to have a master. So in that case of from this, so for example, if we are number 14 and we go to 12, then this master has no more master. No, wait. Now, okay, so this is okay. So you recognize. Let me see. It's one of the more annoying parts here. Okay, so let me before we spend the entire weekend on this, just get to the thing. If the solution is if my rank divided what is this called? Master offset times 2. Yeah, as long as this is 0, we are going on. So, what's the meaning of this?
Sorry, can I make a question?
Yes.
If you start MPI with MP16, for example,
Yeah.
it's from 0 to 15.
Yes.
Okay. So I guess in the first condition should be number of processes with all the dividing lecture, and you keep the operator like as is. I might be wrong.
What are we talking about? Are we talking about line 72 or 65?
65, and so just like.
Okay, so I suggest we return to line 65 later.
Okay.
Yeah?
Sorry.
So, because we are now in the other line. Okay, so my rank. So the process, so what we have to decide is whether we ourselves have to decide whether we are still a slave or whether we are still a master or we have become a slave. Yeah, so, and we become a slave once that my rank, so our own rank, is not dividable by the master offsets times 2. Then we'll become a slave. So let us see here. So for example, we are here in 12. We are the process, say we are the process number 12. We have my rank, so we are counting up. So we start with 1. We divide 12 by 2, we end up at 6, means we are still a master. Yeah, so then we count offsets again, so we'll have offset number 2, multiply by 2, we have now offset 4. Now we divide okay, why doesn't it work? So we divide by my rank by 4, which is 3. So which there is no. I made a mistake. Why don't I? Yeah.
A question. So the idea is to have a for loop to replicate. For example, the first step is going for master. It should show 0, 2, 4, 6, 8, 10, 12, and 14, right? And for slave, it would be 1, 3, 5, 7, 9, 11, 13, 15. Then the next step, we should have 0, 4, 8, and 12 for master, and 2, 6, 10, and 13 for slave. The next step 0, 8.
You know, you're talking too fast because I don't know where you are.
Oh, sorry. So for the
Where are we? In 8?
uh-huh.
Are we in 8 or?
I'm seeing this from top to bottom.
Yeah.
So the first step, we need, just for the masters, we need to have somehow in a for loop 0, 2, 4.
No. So why are you doing it this way? We are not ordered horizontally. We are ordered vertically. Yes, we are ordered because you see these are here the different ranks. Yeah? And we can only, each rank can only control its own work.
Which rank counted? Yes.
Yeah, so we are the loop is vertically.
Okay.
Yeah, so here, so for example, I've taken out here example number 8 in this picture. So then the red ones are the ones that are doing the sending, and here the number 8 is the one. So now we are looking at where are we going to send stuff? Where are we going to wait? Let me see. So we have been receiving, yes. So we are looking at where we send stuff. Yeah. Now we are the slave, and we want to know the index of the guy we are sending to. Yeah. So for example, here number 12 is sending to number 8. So, and I just recognized that what I wanted to say didn't really work. So in the first in the first instance, number 12. So I take my rank, 12, and divide this by 8. Oh man, I divide this by 2, which is of course 4. So I'm still. Well, why didn't it work? I'm dividing it by 4, so I'll end up as still being a master. So then I'll increment my offset to 4. To 4, and then I multiply this again by 8, and then I have a reminder when I divide by 8. When I divide 12 by 8, and then I have to stop in this place. Then I have to stop in this place and say, so this is now my master, where I have to send to. Okay? So, confusing?
Can you go back to the... I have a question on all the receiving, but it's...
Where should I go to? Here.
For example, at least with the code we have right now, everybody is expecting to receive something from my range plus the offset to the end.
My rank, yeah.
So if I'm number 3, for example, I expect to receive from 3 plus offset 2, it reaches...
Now, if I say 3 is not receiving anything.
Exactly. But using this code right now, it should expect to receive something. Like nothing says that number 3 shouldn't receive something.
Okay, but we are not.
Going in this code and
Yeah, but the thing. Okay, let me. We are jumping around because we were currently trying to do the sending, and you keep discussing the receiving.
Sorry.
Yeah, so I mean.
It seems too wrong for me and just like kind of.
Okay, you know what we do. We are almost done. Yeah, now we have calculated our index, our master offset, and we are not doing anything because all we wanted to do is to calculate the master offset, right? And then we do the sending, and then we return to the receiving, yeah, because we are already done. So almost done, almost done. MPI sent. Send. So we'll have to send our result. We send 1 MPI double. And now where to send 2? We send to my rank minus the offset. And the offset we called master offset. Master offset, then we have to add this tag, and then we need to use the communicator, MPI com world. Don't forget semicolon. So then we have our result. We are done with this, and result equals so okay. Okay, so yet now we have done. We've implemented the stuff. let me save it and let me try to compile it. MPI C++, MPI C++, what is the name of this file? Main D and Q, why did I call it this way? Main, am I actually in the right folder? MPI C++ main drq.cpp. So, call it pi, what have I not yet done here? D and conquer, okay? Why not calling it this way? So it compiled, at least. Should we try it? See, because we are not good in theory, so although maybe we are better in trying out. Try and conquer, yeah? So MPI run minus MP. So how many do you want? 16. 16, and then what is it? That's pi. No, not that way. Pi D and C. Let's just command not found. MPI run. Sorry. So, an error occurred in receive.
The MPI still should be in the for loop, the last line.
MPI send should be in the for loop. No, it should not.
It should not.
No. Huh? No, because you see the sender. You have only one master, so you send only once. The loop is only to calculate the index you are sending to. And you see, this is also why the offset is not defined in the loop, yeah, because I could write now int here, so then it would go at the end of the loop, it would go out of scope, yeah, and would disappear. So because I defined it outside the loop, it remains alive after the loop. So, but the problems that we have is, and you know your colleague is always pressing here, with the receive. So receiving didn't work. So maybe this here was not correct. So what should we do instead? I think this is probably the most, yeah. This is the hardest. So okay, so the only two hard things that you have is the one here and the one there. Yeah.
If you start in 3, for example,
you shouldn't do anything. Yes.
So can you go back to the?
I'm where to?
The divide and conquer slide.
That one? No, that is the wrong one. This one.
Yeah. So there are some cases there that you shouldn't walk at all. So it's 3 in this case, right? 3.
So yeah, so if you're a slave, you shouldn't receive anything, only punishment. And if you are born a slave, you don't get anything, right?
Yeah.
So, but you see, you can still have this in a loop, just that that this condition is never fulfilled. Right? So if you are, for example, process 3, then the condition should never be fulfilled, so it will never go into the loop.
Yeah. So I wouldn't say it's a multiple option because in the other cases it would be like in the other steps, but initially it's something like that would be.
Okay, so I mean there's one thing that is probably simple. Let's see, what error occurred? Let me see whether we can invalid rank. Yeah, okay, so what would it mean if we have an invalid rank?
You start as a slave, you are a slave.
No, forget about slaves. Now, what does invalid rank mean?
Maybe in this heat you have passed an invalid rank as a source.
Below 0, above.
Yeah, so it cannot be below 0 because you use my rank plus something that is positive.
Yeah,
Yeah.
it is told that the error occurred in MPI.
Yeah, so this means this here was too large. So how can we make sure, first of all, that the rank exists? Yeah. Let's try this one. So the rank must exist.
Should be
So the offset
number of processes.
number of processes.
This is intervals.
Sorry. Number of processes.
But that should work already, right?
No. I mean,
Because initially the number of processes is from 0 to. Well, of course it's not gonna work.
okay, it does not gonna work. So, okay, it does because this works only for process 0, right?
Process. Yeah.
So now, because we are talking about offset, what's about minus my rank?
Yeah, should work.
If we type it correctly, then. Okay,
Already should cover the slaves at the guess. No?
I don't know. Let's just give it a try. It compiles. And I have to write it runs, but it runs forever.
Yes.
So Control C.
Waiting for
Maybe it's a deadlock.
Yeah, so obviously there's a deadlock. Yeah, so because we want to, apparently we are receiving something, we try to receive something where there's nothing, from where there's nothing coming. Okay, but we didn't get an MPI error. We just made a deadlock.
deadlock.
Yeah.
How?
How did we deadlock? Yeah.
Yeah.
Okay, so that's the question. How did we deadlock?
I don't.
You guys know something? Well, yeah. Okay. Well, probably we have 11, 20. Okay. So we're going to solve this and then. Okay. So how did we deadlock?
I don't think there's a deadlock.
So you don't think there's a deadlock?
No, it's probably some. No.
It is just didn't.
Receive. Some node is waiting to receive, but it doesn't receive anything.
This is what we call a deadlock.
But deadlocks when you have like a circular dependency, right? There is no circular dependency there. It's one of the conditions. If it's just like nobody's supposed to send you anything anyways. So
Okay, so you don't call this a deadlock, but still you're locked.
Yeah, it's a lot because someone's waiting
I
for
think somehow one of the slave and masters, the source and destination rank are mismatching, and that
Yeah,
is
so
not happening, and everything is just stopped.
so who got the
Yeah, I'm getting the result, but I'm getting a huge error.
Can you put another repetition?
yeah, for example, I mean, for example, the number 3. Yeah, you always came with 3, right?
Yeah, it should not receive anything.
So, and then
And some other numbers.
then number 3, yeah, so, but this is not, you see, number 3 is the one that blocks you. Because it believes it should receive something.
Yeah.
But it does not, you see, because if he said, my rank is 3, and we have 16 minus 3, yeah, it's something like 13, and the offset starts from 1, so it's trying to receive something, but it's not supposed to receive anything. Okay? So, this means the condition is not wrong, but the condition is not sufficient. So we need another condition. What other condition?
My rank should be I don't know how to say this operator, but it's the same as
This one.
Yeah.
So this is the modulo operator. Offsets. Okay, so it's again the same thing as before, and this, as long, see,
Yeah.
as long as this is, so if we can divide this. Okay, save. Let me see. And let us run. So it ran. It actually ran. Because we had 16. So will it also work with 15?
Probably not.
Probably not. Let us see. It worked. So I think that the reason why it worked, let me see what we can do. So, I mean, we had this condition that we are not supposed to run out of the domain, right?
So it should be using like 8.
So let's take this out and try it again. Compiling and running with 50. So this didn't work. The other one, sorry, but I believe this will also not run with 16. This will also not run with 16. No, we need this condition. Okay, so it worked. So why did it work? I think this thing here helped us that it worked. If we go back to the lecture. So what do you do if it's not a power of 2? Pretty simple. You'll skip here. Yeah, and asking whether the guy you are expecting something from actually exists. already skips. So if we have this condition, looking for whether my master here is, or whether I have a slave, whether there is an index from at the position where I have my slave, yeah. If this is not the case, it will automatically skip this, yeah. So, and because it automatically skips, it's probably not running optimally, yeah. But it's so the as we say, the tree is not balanced. It has more leaves on one side than on the other side, but still this works automatically. So then, as a last thing, and I think we discussed this already with most of you last time, instead of what we have implemented here, we can also just use the reduce method. You can just implement it as a reduce method that does basically the same thing. There's also or reduce. We've already indicated this. No, I don't have the functions here. Okay, so most of you have already implemented this, so probably because we are now 11:15, we'll stop this here for a small break and go on with the second part of this in how many minutes? Sorry.